Hello, everyone. Welcome to Deep Learning Design Pattern Study Jam, session number 4, organized by GDG Seattle. I'm Margaret, the lead organizer of GDG Seattle, and I'd like to welcome you to our event. And for those of you who are new to GDG Seattle, we are an inclusive community where everyone is welcomed. And our motto is be excellent to each other. If you see or experience anything different, please contact us, GDG organizers. So here's today's agenda. First, we will just introduce the instructors and organizers, and then we will do a very quick review of session 4 review, and then we'll go to open Q&A and then wrap up and talk about next steps for session 5. During this session, please post your question to YouTube live stream, the chat window. Feel free to add your comments, and we'll try to be as interactive as possible. In the same time, if you could just copy your question into that doc for us to keep track of all the questions, that'd be great. Feel free to use the hashtags and Twitter handles below. So please welcome Andrew Ferlitsch, our instructor for the study jam.
Hello. Thanks for the introduction, Margaret. As you know, I'm Andrew Ferlitsch. I think most of you have already met me from earlier study jams, but if this is your first time, I'm part of Google Cloud AI Developer Relations. That means I'm external facing. In the pre-pandemic period, you'd see me physically out in a lot of places, like at conferences, doing workshops or training or presentations. Sometimes I was at universities as an adjunct professor, do meetup events like this one here, and just a variety of training workshops in software communities, and also working with some of Google's largest enterprise clients, helping them get over large-scale production issues with machine learning. My expertise is computer vision and deep learning. I was formerly a principal research scientist for 20 years, and I have 115 US issued patents based on my research. And I'm currently writing a deep learning book to be published by Manning. So back to you, Margaret.
Thank you, Andy. And just to mention, this study jam is based on Andy's upcoming book. And I'm Margaret. I'm one of the instructors for the study jam. As I said earlier, I'm the lead organizer of GDG Seattle. I'm also a machine learning GDE, Google Developer Expert. I also lead another group called Seattle Data Analytics and Machine Learning. Currently, I'm working on AI for art and design. And here we also have another GDG Seattle organizer, Yinchi, who's helping out.
Hi, I'm Yanchi. I'm helping this. I'm a co-organizer for GDG Seattle and helping out this session. Yeah, I'm an Android developer, and I did some project with machine learning, like around the engineering side. So that's me.
Thanks, Yanchi. So prior to this, for those of you who are new, hopefully you've already been here before, the format of this study jam is that you will study by watching the videos, and and we also included the slides here. And for this particular session, we don't have the workshop links, and Andy's still working on it. And you should have studied the 3 topics: autoencoders, hyperparameter tuning, as well as transfer learning. And next, Andy is going to spend just a few minutes for each of the topics just to do a quick recap.
Okay. Yeah, we're changing the format this time to try to make it a little more interactive. So for all 3 of them, I'm just taking a single slide and just do a quick review before we answer any questions. Okay. So you read about autoencoders. It's a different type of model. And the whole idea behind an autoencoder is actually unsupervised learning. That is, you don't have a data set where you're using the labels. Okay. Instead, you're learning some transformation of the data set. Okay. And the simplest version of it, we call it learning the identity function, which people associate with compression and decompression. What's the best way to compress these images and decompress them? And so you always start off with on, let's say, the left side here in an autoencoder with the encoder part, which is gradually lowering the dimensionality of the data. It's getting smaller, 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 and smaller. So what we're doing is we're doing some form of pooling, but we're not doing a static algorithm. We're doing a convolutional layer, which means that we're doing feature pooling. So we're learning the optimal way to decompress or make the data smaller and smaller until we get to what we call sort of the middle part of the network of the autoencoder, which is our latent space. And then we just invert it on the other side. So now what we're doing is learning the best way to unpool it. So we're going to do a deconvolution each time. And we're going to gradually, as in the identity function, make it bigger, bigger, bigger until we're back to exactly the same size as the input. So what becomes our label here? The input is the label. So we give it, image X here. What do we test it by? The same image X. So the image itself becomes the label. And this last step of putting it all back together is what we call reconstruction. And that's what we're learning. And in autoencoders, we can do all kinds of ways of reconstruction, use it in different ways. For example, a popular one is super resolution. So how do you take images of one resolution and increase them to a higher resolution and not have artifacts and all the regular things you would have with a static algorithm, but learn how to actually make them really super high resolution and really high quality. So what you do is you take a data set that already is super high resolution. That's your input. You intentionally physically downsize them using a static algorithm. And so the downsized version, actually, I said that backwards. The downside version becomes the input. The original super resolution images become the output, and you learn this reconstruction. I guess the other point here to point out is prior to this, all the models that we were showing so far were image classification. And basically, they were doing what was called representational learning. And in autoencoder, you got two parts now. You got the representational learning, which gets you down to the latent space, which is like the bottleneck layer in an image classifier. But now you have a whole new section to the model called transformation learning. You're learning how to transform this latent space into something else so that you can do some reconstruction task. That's probably enough there.
Yeah. So basically, like what Andy said, up to the middle part, this is really kind of like what you've all done with image classification, right? You're doing some sort of downsampling or feature extraction here. And then starting the middle point, you do like the upsampling, right? Which is kind of opposite of what you do with the image classifier. So that's a great recap. Thank you, Andy.
Okay. I'm looking at our little document here. Somebody has one question, so I'll read it.
Okay.
Are there any applications such as regarding the audio encoder's output as image or audio data with proper network arrangement? I'm not exactly sure what they're asking for here. I think they may be asking, are there any practical applications for autoencoders?
I'm not very sure about what proper network arrangement means.
Okay.
Like, I didn't quite understand that.
Okay. They may want to update their question, but in the meantime, I'll just make an assumption or talk about practical applications. The super resolution is one of them. Actually, one of the things we use autoencoders for, another popular thing is improving the quality of images, like noisy image or grainy images. So you can take, one of the sections in there in the book in that presentation was showing you how to use an autoencoder where you're actually learning the identity function, identity plus epsilon. okay? And the epsilon is the noise. And so we take a bunch of images and we add some random noise, like to make them a little bit grainy. Okay, that's our epsilon. And what we're trying, the reconstruction is the original X. Okay. And why could this be useful? Well, you know, with our mobile cameras, they're great cameras, but we're not always under the best picture taking situation, are we? It might be a little dark. The lighting may be a little weird. I mean, come on. Not all our pictures come out great, you know. So this is another application of how to improve the quality of pictures. The place where I use autoencoders, okay, is I actually break them up. The encoder and the decoder have different functions, okay, and I'll use them. I don't go into a later section, we'll go more into it, but I use them for what's called pre-training. Okay, I may, like, for example, let's say I got this data set, and what I really want it to do, what my model to do, is learn the essential features from the data set so it can generalize well. Okay. And so I could do some unsupervised learning. Okay. I could make my encoder effectively the head of my model. Okay. Then I got this decoder over here, right? And then I might give it some interesting task, like the popular one is the jigsaw. You take your image and you break it up into 3x3, so 9 different segments, and you randomly permutate it. And you're trying to learn how to reconstruct that image, and that permutation is the label. Well, it forces the network, the representational learning, to effectively learn what's the real features here. So I got it trained on that pretext task. I then tear off my back here and I put on the rest of my convolutional neural network, and I continue now back to training in supervised mode.
Yeah, and that's a great point. I also want to add another kind of application to how autoencoder can be useful is that if you have heard of like visual search, like visually searching images, you could also train an autoencoder and then use the encoder part as a feature extractor, and then calculate like the similarity distance among the images, and then find similar images that way. So I see that in the document, there's another question saying if you have completely brand new data set, for example, with analogous input and output features, however, with different dimensions, is it always worth to use or modify an existing pre-trained model?
Okay, I think that goes along with the for transfer learning. So maybe we're better answering that when we get to that.
Yeah, maybe that sounds good. And then there's another question saying for hyperparameter tuning. So we can also wait until when you talk about hyperparameter tuning. So are there any more questions about autoencoder?
There's update to the question.
Oh, to the question that we need. Okay, are there any applications such as regarding autoencoder's output as image or audio data with proper network arrangement updated, such as the source of another image or audio training data set, or making association has to other sorts of image or audio? I'm not quite understanding this.
I think Andy and Margaret actually kind of answered this question, because you guys actually mentioned the application of like the input encoder and decoder part. So
what we use it for, right?
Yeah.
Okay.
Yeah, I mean, one trick I once used in autoencoder. So the ResNet 50, the way it's designed, when you give it images that are a size 224 by 3, when you get to the bottleneck layer, the final feature maps are all 4 by 4. So you got 16 pixels. Okay. And that's big enough for that final stage. But if you were to take that same ResNet 50 and you would use it on CFAR 10, where the input size is 32 by 32, well, before you get to the bottleneck layer, all your feature maps are 1 by 1. They essentially lost all their spatial information, and you can't learn from it. So what the back then what the ResNet authors did is they wrote a special version of the ResNet network, particularly adapted to that input size, and they were able to get, I forget, it was a certain percentage, accuracy after 200 epochs. And what I did is I said to myself, I bet you I could solve this problem differently. So I took a ResNet 50, an untrained one, just a generic one, and I put in front of it a decoder, okay, that learned the optimal way to increase the input size from 32 to 224 to 224, okay, and I just put it as a pre-stem in front of the ResNet 50, trained it with that, and in 200 epochs, I got the same accuracy as in the paper. I didn't have to write a special network.
Okay, great. So I think that's it for autoencoder. Let's move on to the next area, which is hyperparameter tuning.
Okay. Yeah, this was probably a really big area for you guys. A lot to cover, a lot to digest. So this is just kind of a summary. For me, I work with convolutional neural networks. So the primary things I need to tune are going to be, the initial learning rate, the learning rate schedule, and the batch size. Those are the big three for me. Okay. And, if you were, read or you through the presentations, you've learned that training has changed a lot. We don't take one model instance and we just train it from scratch and say, ask ourselves, is that a good one or not? And if not, start all over again. Okay. So we go through these various stages, and you call them warm up, pre-training, and then the actual final model training. And each one of those stages, we might be doing multiple instances. So we found that the actual initial weights or the distribution of weights at the start in the model can make a big difference of whether the model will converge or will it converge on a good optima. And that's called having weights that are numerically stabilized. So we discussed a number of different techniques for this sort of warm-up training. For numerical stabilization, one of them being the lottery method, the other one being sort of the more traditional warm-up, where I have this tiny warm-up rate, and then there's my initial rate, and I slowly increase it for a handful of epochs, but they're short epochs, and I'm trying to get the weights to shift around and adjust relative to each other, but in tiny amounts so that the model stabilizes. And then I got a good numerically stabilized model, but I haven't actually trained it yet, even though I'm using my training data. And that puts me here. Now I want to learn what is the best, hyperparameters. What's my best learning rate? What's my best batch size? And even within that, once I got those stabilized, what's my best learning rate scheduler? What's the best way to change the learning rate as I go? So I'm going to have, again, multiple instances of this going on. And finally, I'm going to find that right combination. And the one with the right combination, that instance, that's the one I do my actual model training with. No, I did notice in the door, somebody asked a question relative. Let me read it. Okay, for hyperparameter tuning, when you are using some training data epochs to identify the optimized weights, which is what we're talking about, can you also use the same epochs to do other training tasks, or can you only use that set of epochs for the hyperparameter tuning? Okay, so I would say the answer to your question is yes, because if you look at the warm-up, right, the end result of that instance I've kept is because of those epochs. So in a sense, I've retained those epochs. I didn't lose the value in finding that numerically stabilized one. Now, if I did the lottery method, yes, on the ones I threw away, yeah, that's discarded epochs, but on the one I kept, it is not. Same thing here in the pre-training. Let's just say hypothetically, I do 20 different instances, okay, different combinations. Yes, the 19 I throw away, I've thrown away the effort of those epochs, but the one I kept, it's retaining the benefit of those epochs. Did you want to make a comment, Margaret? Okay.
Sorry, no, I was kind of distracted. By the way, I want to say hello to Balaji. Balaji is in the attendees. He's also one of our other co-organizer of GDG Seattle. Just want to say hi. So there's this question. Sorry, I wasn't really paying attention. I was doing something, trying to update the site. Yeah, did you already answer the question?
Oh, no. It's actually a really good question. Until you've done your hyperparameter training, how do you know what the initial learning rate is? Okay. So that's a problem, because part of warm up is you have this assumption what the initial learning rate is, and then you go to something really tiny and you work up to it. Okay. You just have to guess, and so I always use I make the assumption on the low end of an initial learning rate. So I'll use like 0.001 or 0.0001. And then I'll make my initial warm-up rate 1 to 2 magnitudes smaller.
Okay. So let's look at the document.
Yeah.
There's another hyperparameter tuning question.
Yeah.
When you are using some training data epochs to identify optimized weights, can you also
Andy answered that.
Yeah.
Oh, you already did. Oh, that's the one you answered before this, right?
When I tried to set a training rate other than a default one in Keras, the performance of the network got worse. How does Keras determine the default learning rate? Okay, well, for most of the optimizers, the default learning rate is 0.001. Believe it or not, by just chance, for image classifiers with standard stock networks, it's a good starting point. Okay. A lot of times you're going to be in that ballpark. Okay. So if you don't know any better, that's like the best one to start with. Now, in my presentations, you'll find that when I use my own homegrown way of tuning and not automatic tuning, I kind of make that number the center point. And then I got a magnitude, 1 or 2 magnitudes less of one direction, 1 or 2 magnitudes more in the other direction. And I'm doing a divide and conquer approach. Okay. So I don't want to have to try every possible combination. So I kind of divide the space in half, try some examples and say, what's my best result here? Take the other half of the space, try the same thing. What's my best result here? Whatever side is the best, I just go there, throw this out. Then I'm going to take that space, cut it in half, and the same thing. Now, when you're doing, let's say, automatic version of hyperparameter tuning, like the Keras tuner, and you use the random search, you probably saw from my pictures, I kind of visualize the search space like a big volume, a big cube. Okay, like a big empty universe. There's a planet here and a sun there and so forth, but most of it is empty, and most of that empty is the unoptimal space. Okay, and then there's little specks, you could say, planets that are the good hyperparameter settings that give you optimal results. Okay, very sparse, but they're within solar systems or are quite much better. And anywhere in that solar system, you would get a near optimal result, better than the blank space. Okay. Well, the reason random search works, because you first think, if I just did that randomly in that almost empty universe, I'm not going to ever find a good set of values. It's just going to take forever. Okay. But it's kind of a beam search. Okay. What you're really looking for in that first round is to land into, I said, the equivalent of the solar system. Where you're getting that near optimal result. Because if you land in one of those areas, within that area, you're likely to find a planet, the good optimal results. And so you do all this randomness and you're looking at your results and you're looking for those beams. Every one of those trials is a beam. And and you're looking for, which ones meet the criteria of a near optimal result. Then you reduce your search space to just the space around them. Suddenly you've gone from this big universe to the space that's equivalent to a solar system, and you just do beams within them. And that's why random search can work efficiently. Okay, so let's see if we have any more questions on that. I think we've covered the hyperparameter tuning. Maybe we should go to transfer learning.
Sure. Just give me 1 second to reshare the screen.
Okay.
Oh, the screen is shared. Okay. Let me just put it on full screen.
Yeah, while you do that, and before I start, maybe you can offer a tip or two you have about hyperparameter tuning.
Yeah, I think we can move to the transfer learning here. Actually, okay. I can talk about the hyperparameter tuning part. Just one thing I want to mention. I don't know if you mentioned it in your video about did you talk about the batch size?
Oh, yes.
Okay. Yeah. So did you talk about the batch size, like what batch size to start? Like you say start with 32, and as you increase the batch size, if it's bigger, it trains faster, but sometimes it also might overfit. And also you increase the batch size, it also requires more of the memory, right? So
right. But we also have found there is a correlation between the batch size and the learning rate, really an inverse. Okay.
Yeah.
And it used to be we train with a fixed batch size, even though we're changing the learning rate. Okay. But because the batch size is correlated to the learning rate, we now dynamically change the batch size as we're changing the learning rate. But in most cases, what it means, because the learning rate is going down, the batch size is going up, which means we're more smoothing out the differences, right? So the weight updates are getting smaller and smaller and smaller. And because of that, we're less dependent on noise for generalization. Okay. Actually, keeping noise high at very tiny weight changes will keep the thing from that final convergence. And so at the same time, now when we train, we make regularization dynamic. My learning rate's going down. My batch size is going up. As it goes up, my regularization is going down. All these things are fluid in play, whereas just a few years ago, they would have been fixed values.
Yep. So I'm going to move to the next one about transfer learning now.
Okay.
We're not seeing the slides.
Yeah.
Oh, you're not? Okay.
No.
Sorry.
Okay, there we go. Yeah, this is my big one. Okay. There's two types of, really two categories of transfer learning, but they all start with the same assumption. There's a pre-existing model that's been pre-trained, okay? And it's a really good quality model. Can I reuse it, okay, from my data set? And so we take this in the context of an image classifier, okay? And so there's a lot of stock models out there that have been trained on ImageNet, which is 1.2 million images on 1,000 categories, everything from people, breeds of dogs, and so forth, okay? It'd be unbelievable, all the different categories in it. But in doing so, that existing network, basically, you could say the vast majority of the network is involved in learning essential features, doing feature extraction from images, and learning the essential features to build that latent space. And in transfer learning, what you're saying is, hey, that latent space, which is also referred to as the bottleneck layer, is reusable, okay, for other purposes. So in the simplest case, so if we take the main part of my network, I'm going to keep it, is the very end of my network, which they also call the top of the network. So where you the output is the top, the input is the bottom. That tends to be confusing to people, okay? But the top, which is the output, you have those last two sections. You have the bottleneck layer where you're going to do your pooling and flattening. So you pool the remainder feature maps, and then you flatten it into a 1D vector, and then you do your final classifier. So what I can do is tear these off, the pre-trained one, put new ones in, and just retrain them for my specific problem. So in a sense, what I'm saying is these final feature maps here are essentially reusable, okay? Now that works in two areas. I got a big, massive network that's been trained on a massive diverse data set like ImageNet, okay? So it's likely my problem is somewhere a subset in there. Or the data set it was trained on is very similar to my data set. So think of this. Let's say you had a data set trained on fruits, okay? And now you want to build a classifier trained on vegetables. Well, you know, vegetables are probably a lot of things, have a lot of similarity to fruits. It's probably, I could just reuse that smaller network trained on fruits, tear off the bottleneck, or it's also referred to as the pooling layer, and the classifier, put on my own pooling and classifying layer, and retrain it. Now, sometimes my data set is so unique, it's kind of as distinctive parts from what the train one is. That is, this last part here, it doesn't fully, it's close, let's just say. It's got most of the essential features, but not all of them. Can I still reuse this model? And the answer is yes, it just takes more work. So we started in this multi-stage thing here. So I start off the same. I tear off the top, and I keep this part of the model frozen, and I take my data and I train a new top. Okay, so it's getting close, right? And then when I'm done training that, I then work backwards. I'm going to unfreeze this layer. This becomes my tuning. Okay, and I'm going to train it again. Now tuning this group, convolution group, relative to the top. So that gets more closer, the feature extraction here, and then work backwards, do that, work backwards, do that, work backwards, finally on the stem. But these are generally very short epochs. So for example, if the original training here was 200 epochs, these might be as little as 10 or 20 epochs. Okay, let's see if we have any questions. Okay. There's the one in Hyperparameter, auto. Okay, so somebody asked here, if we have a completely new data set, analogous input and output features, however, with different dimensions, is it always worth to use or modify an existing pre-trained model? And it really comes down to what's the size of these feature maps right here. So these models are generally tuned for a specific spatial size of those feature maps, okay? And so I gave an example of the ResNet 50, which is a very popular one to reuse, okay? So at the 224 by 224 image size, the size of these final feature maps before they're pooled and flattened are 4 by 4, 16 pixels, okay? If the input size gets too small and there are 1 by 1 by the time they get here, it's not going to work. So for a ResNet 50, you basically don't want to get below 128 by 128. So you have to know sort of a little bit about how to calculate the input size. But if you're using one of these built into the TensorFlow Keras, okay, where from applications you get it, and you can specify the input size when they give it to you, okay, and it's already pre-built, just do a model.summary and look there at the very, very end, and look, you see, go to the bottom. The last thing is your softmax classifier, right? The next thing above it is going to be like a global average pooling, your flattening pooling layer, and the next thing above it is that final convolution, and you look at the output size. And as long as they're at least 3 by 3, it's going to work. Did you want to make any comments on transfer learning, Margaret?
Yeah. So I was adding a slide earlier to the I was adding an additional slide to the deck. Is that I recently made a transfer learning course unpacked. For those of you who actually have the subscription, you should definitely check it out if you're interested. So I actually went in depth talking about transfer learning. I talk about TensorFlow 2.0. I talked about how to do transfer learning using tf.keras, and I also talking about transfer learning using TensorFlow Hub. For those of you who don't know what TensorFlow Hub is, that it's a place. Just search for TensorFlow Hub, where you can find all kinds of pre-trained models where they can be in saved model format or the TF-Lite format or TensorFlow JS format, and you can use those pre-trained model as it is, or try to fine-tune it, or using it as a feature extractor. And then the last part of the course, I actually talk about transfer learning using TensorFlow Lite, where one is actually TensorFlow Model Maker, where you can just feed in some your own data, and the TensorFlow Lite Model Maker will create the classifier for you. Underneath is the efficient net underneath, and you can also change it to other network architecture as well. And then I also talk about on-device training, actually machine learning training on Android mobile devices, and how that's possible to actually use transfer learning.
Okay, that's great.
Okay.
I did see another question. Somebody actually is asking about an NLP question.
Okay.
Transformers. Okay, it's not really my area of expertise, but I can offer some insight. What made Transformers special was the idea of attention. Okay, before Transformers, natural language was handled as a recurrent neural network. Okay, and that, just to oversimplify it, to answer something, I had to sort of know a sequence of things. Okay, so think of an image classifier. I only look at the image. I look at it once and I figure out what it is. I don't have to look at a prior image and a prior image and a prior image. So there's no sequence information. But in a sense, there is. Okay, what attention did was allowed to look at a large amount of text as if it was an image. And so there's no recurrent network. So in fact, it acts very similar to an image classifier. And attention actually has changed how NLP models are designed, that I would say they're even moving in a similar model idea as it is in the imaging world. Oops, there's something there.
Yeah, we have one question from chat.
Okay, since the deeper layers are looking at more abstract features, wouldn't we be getting rid of that information when stripping the last layers? I'm not sure what they mean by stripping, probably pooling. Okay. Well, we still...
Sorry, my unmute, it wasn't working. I can answer that question.
Okay,
I think when this person was, Asim was asking about stripping the last layers, we're actually talking about the very last layer, which is the classifier, which is very specific to the problem you're trying to solve. So let's say if you train a classifier that's classifying dogs, and you try to do pre-train, try to use that for transfer learning, we want to take out that classifier part, because since that's for cats only, right? You want to do it for vegetable or icons or something else. Also, I think that's what you mean by getting rid of the information of the last layer.
Okay, yeah, so it's probably...
but in fine tuning, you can also specify the layers of fine tuning.
The last layers are not learning any feature learning. they are where you could say it's they're learning a task. And now you're in this case, that task is a classification. In this case, you're replacing one learned task with a new learned task. And there could be other tasks. Well, most of this so far you've seen is in the context of an image classifier, but what's the next type of task you could learn? Object detection. Well, I actually got my model is actually learning two separate tasks in parallel. One is learning bounding boxes. Okay, so the bottom of my model, what it's learning is to make what we call bounding box proposals. These are boxes, boundings, segments of my image where it thinks there's a foreground object in it versus the background. Okay, and then when I'm learning, okay, I'm learning to classify what's inside that bounding box. That's one task. And then another task that's learning to refine the bounding box, to fine tune it. Go to the image segmentation. Okay, it kind of goes a step further. Not am I just figuring out the localized objects. Here are the bounding boxes. Here's what's in it. Here's the best fit of the bounding box. Then I got to color every pixel, right? I got to say every pixel. Is it part of the object or not part of the object? So now I'm learning 3 tasks. Okay.
Yeah, so that's a good point. So what Andy is saying is that the transfer learning is applicable to not just image classification, but also other computer vision tasks such as object detection as well as segmentation. I also want to point out, even it's applicable for text as well, right? It's not just image, like text classification.
Yeah, BERT,
you can do
people reuse BERT and all its derivative since totally reused. And even before NLP models became highly reused, even the pretext task, like word2vec and all that, is itself a model that takes your data, your text data, and converts it into another form that is better to learn on.
Yeah, okay? The embedding.
Those things have been reused for quite a number of years. They're actually in the machine learning world. Lots of things have gotten really good. It's like, why would you reinvent the wheel? So people just reuse them.
Yeah. So basically, transfer learning is a very important concept in machine learning, right? In various areas. Now, this next question is training data size wise for transfer learning. Could I use less data with my specific object to get decent result? What would be the minimum requirement, like 25% of main model training set, etc., etc.?
The general rule of thumb has always been that if the two things are similar enough, 10% is usually enough. But in the case of image classifiers, if your original model was trained on a small amount of data, then it's problematic. 10% of that may be too little. So there's usually some minimum thresholds. Typically, people say for image classification, you should have at least 100 examples in your transfer learning per class. Whereas in the original model, when you're training from scratch, you should have at least 1,000 examples.
Yeah, and that's a good point also, whether your new data set, how similar it is to the original problem, the original data set.
Now, some people are able to work with slightly smaller ones, obviously image augmentations out there, but really I think the big thing are using GANs to synthesize similar looking images that realistically could have been part of that class.
And speaking of augmentation, data augmentation, I think our next session you will be talking about data augmentation in more depth.
Yeah,
right?
As we go into data pipelines.
Yeah. Okay, so let's look at the document.
Okay.
I think we got all the questions, right?
Yeah. I think so. It might be a good, because we're running at 8:20. Might be a time to wrap up.
Sure. So I'm going to move on to the next slide, and we already did the Q&A.
Yeah, we already did that.
And I'm going to just talk about this again, just in case you're new. I think most of you have already been here before, but just quickly to go over, you read the material on Andy's GitHub, watch the videos, and then do the exercises. And then join the Slack if you haven't done so to ask questions, because we're only doing this Q&A every 2 weeks also, right? So if you get stuck with questions until the next session, it's good to have a discussion on Slack. And then for the next session, bring your questions. So for session 5, and there will be the data distributions and data pipelines, Andy?
Yes. And, my cat is joining us.
Yeah, my cat just jumped down. So I think Andy is still working on the material, and also the holidays coming.
The slides are for the first one are ready, and I'm still working on the second part, data pipelines.
Yeah, and also there's some holidays coming up, July 4th, so we can have an excuse to have some time off. Our next session, originally scheduled for July 2nd, we have moved it to July 9th, so you have 3 weeks to study for these 2 areas. But wait, I thought there was image augmentation here.
Oh, yeah, the data augmentation, part of it's covered in data distributions, and another part of it. Data. So when we first re-talked, I've reorganized the material in the section. I've made it more aligned with the concept of pipelines.
Yeah, makes sense. Yeah, instead of just the image augmentation on its own. Okay, great. So yeah, hopefully this is auto recorded. For those of you who missed this session, you can watch the recording. And I hope you all have fun, and we will see you next time on July 9th. Thanks, everybody. Bye.
Bye.